All right, we're going to continue with our discussion of electrophilic addition to alkenes, and we're going to pick up with oxymercuration-reduction. In the last video, in the last lecture, we talked about acid catalyzed hydration. And here we had an alkene. Let me just start again. We treated it with H+ and water. And what we found is that at times we can get a mixture of products. So here we have the rearranged product, and here we have the unrearranged product. If we want to get an exclusive type of alcohol, we can sometimes use what's called oxymercuration-reduction of an alkene. And we're going to treat an alkene with mercury 2 acetate in water, and then we're going to reduce it with sodium borohydride. So overall the reaction looks like this. The first step is oxymercuration. And the second step is reduction with sodium borohydride. We can see our starting alkene is unsymmetric. We have regioselectivity according to Markovnikov's rule. The net reaction is adding water across the double bond, so that we add, this becomes hydrogen, and the OH is where the water added. I'll go through the mechanism so that you can see it in a little bit more detail. Right, so when we do the first step of the reaction, the mercury 2 acetate will add to one carbon of the double bond, and the oxygen of water adds to the other. This reaction is regioselective. The mercury acetate is going to become bonded to the less substituted carbon, and the OH of water becomes bonded to the more substituted carbon of the double bond. We're going to then reduce the organomercury using sodium borohydride, and it will replace the mercury acetate with hydrogen. This reaction is not green. Okay, when you do the acid catalyzed hydration, it's a much more green reaction because you only need a catalytic amount of acid, and you're doing the reaction in water. Here, we do have water, we're using mercury acetate and then sodium borohydride. So the first step of the reaction is to dissociate the mercury acetate. And what this does, it leaves us with a negative acetate anion. And now we have generated our electrophile. Okay, so we can proceed with this reaction the way we would when we do our electrophilic addition. Okay. So if I have my alkene, I have my electrophile. Okay, so what you can see is I put the positive charge on the more substituted carbon. Really, this intermediate is a bridged intermediate. Okay. I say here it resembles the bridge bromonium ion. We'll talk about that in later lectures. So if I draw it for you down here, so really this positive charge is spread across the two carbons. No, I can't erase. Let me do this again. So here is the intermediate I drew on the previous page, and this positive charge can be delocalized. So this is the most stable, and it's the greatest contributor. We have a bridged mercurinium ion. I think I spelled bridge wrong on the previous slide. I apologize. Alright, so now we have our intermediate. Water is going to attack as a nucleophile. And it's going to attack the carbon that has the most positive charge. And that would be the secondary carbon here. Okay. We have an oxonium ion, similar to acid catalyzed hydration. We can deprotonate. And then reduce. So we would add this in a second step. So everything that happened prior was a single step where you have the mercury acetate in water in solution. Then what you would do is you would stop the reaction or let the reaction come to completion and then work it up with the sodium borohydride. So this is a new reagent being added. And here we get our single alcohol product. If we were to compare the two reactions, what you would see is that oxymercuration-reduction leads to a single product. Okay. Both are regiospecific, but there are no rearrangements for oxymercuration. Alright, so we looked at a reaction that gave us Markovnikov addition to make an alcohol. There's another reaction that we can use to make alcohols. It's called hydroboration-oxidation. Okay. The net reaction from hydroboration and subsequent oxidation is again the hydration of an alkene, and we're going to get an alcohol as our product. Here the key difference is that the net regiochemistry of hydroboration-oxidation is anti-Markovnikov, because the hydrogen is added to the more substituted carbon and the oxygen is added to the less substituted carbon. The reason that this works this way is because here we are using what's called BH3. This is a hydride. In hydrides, the hydrogen actually is negatively charged or has a partial minus. So it reacts a little bit differently. It's not the electrophile here. In this reaction, the boron is deficient in electrons and acts as the electrophile. So that this adds to the least substituted carbon. We typically use THF as a solvent for this reaction. It's a very nasty solvent, so this reaction is not green. But it has no rearrangements. Okay? Alright. In addition, this reaction, in addition to this regioselectivity, right, the reaction is stereoselective as well. And what you'll see is that the boron becomes bonded to the less substituted carbon. Okay? And then the hydrogen and the boron are going to add to the same side of the double bond. I didn't mention this previously, but when you have a bridged intermediate, I think I mentioned it in class, the water comes from the opposite side of the bridge. Okay. Here in hydroboration-oxidation, it's going to be a syn addition. Okay, this would be anti-hydroboration-oxidation is syn. So if we looked, let's look at the mechanism of this. I'll do it on a. So when you look at the mechanism of hydroboration-oxidation, here's my alkene, and it's asymmetric. Here's my boron. Here we have attack of the boron. In a concerted process, so what this means is that at the same time that the alkene is attacking the electrophile, the hydrogen can add to the alkene because we have a partial positive charge there. This results in the following intermediate, where we have a partial bond between this vinyl carbon and the boron, and a partial bond between this vinyl carbon and the hydrogen. Now, we're breaking a pi bond, okay, and we're also breaking a boron hydrogen bond. So this is our transition state, okay, and then what we can do is we get the following intermediates. Okay, this will happen 3 times. So that we get what's called a tri-alkyl borane. And then what we can do in the second step, we can add peroxide in NaOH and oxidize so that the B becomes OH. Okay, I failed to write the overall reaction, so let me do that as well. Our starting alkene looked like this. In the first step, we add BH3 and THF. Once the reaction, that first step, is to completion, we can add peroxide in the presence of NaOH, and then we are able to obtain our alcohol. Alright, if we look at this, it's anti-Markovnikov, and we have syn addition. Alright, let's just do another example. You're not going to be responsible for this mechanism. Okay, but I just wanted to show you the mechanism so you could see where everything was going. Alright, so another example. And I'll step this one through the entire mechanism just so that you see where everything goes. First, I'm going to write the overall reaction. As you see here, I get a racemic mixture of products. But what you should also note is that the OH and the H are on the same side of the ring. Okay, so just to show you the mechanism of this reaction, we have our asymmetric alkene. We have, in the first step, we add our borohydride. Okay, so we have electrophilic addition, where the alkene is the nucleophile. Okay, the electrophile is the boron. At the same time, we're going to break the boron hydrogen bond. Okay, now we still have two hydrogens, so we can have more alkene in the solution. Same thing happens again. Okay, and then finally it will add a third time so that we get a boron, a trialkyl borane. In the last step of the reaction, we add peroxide with some base. We're going to oxidize, and we get the following alcohol. Here I didn't indicate any stereochemistry, but what you should note, similar to my top product, that the OH and the hydrogen here are on the same face of the ring. Okay. What I'd like to mention is that when we reduce, we are increasing the hydrogen content. So think about the oxymercuration reaction. Okay. We took the mercury and we reduced it to a hydrogen. When we oxidize, we increase the oxygen content. Okay, so here in the hydroboration, we oxidized the boron to OH. Okay, so I stepped you through this mechanism, so here's just a lot of text. Alright. Now let's move on to the reduction of alkenes by hydrogenation. So this is section 9.7. Alright, so what we can do is this: if we have hydrogen metal in the presence of a platinum catalyst, we can add hydrogen across the double bond. Okay, now we take our alkene and now make an alkane. Here we're adding hydrogen to each vinyl carbon, so regioselectivity is not an issue. We do have stereoselectivity, where the hydrogens add syn to each other. The reason for this is that this is a solid catalyst, so it will physically block one side of the double bond, or one face. This reaction is a net reduction. As I said before, when you add hydrogen, it's a reduction. Okay, so you need a catalyst to get this reaction to go. Otherwise, it takes very high temperatures and high pressures. Alright, the catalyst can be platinum and palladium. We can also do this with a nickel catalyst. Okay. And so what you'll see is that the more accessible face of the alkene will approach the catalyst, where you have the hydrogen bound. Alright, so now alkenes are more reactive than other functional groups with double bonds. Okay, and so here we're going to hydrogenate just the carbon-carbon double bonds. We will not hydrogenate double bonds in an aromatic ring. So for example, if I gave you this molecule and I told you we added H2 over a platinum catalyst, your product would be the following. This stays intact. The reason is this is an aromatic ring. They are not isolated double bonds, whereas this was an isolated double bond. Alright, I'm going to go through section 9.8 later. Words regarding hydrogenation and catalysts. So a catalyst is going to lower the activation energy, and you take a different path. Okay, so let's say this is the reaction without a catalyst. With the catalyst, you have a different path. The use of chiral catalysts can allow for the formation of chiral products. Here you are organizing your reagents, okay, so that they are in a fixed orientation to the catalyst. And as a result, you can favor the formation of a particular stereoisomer. Alright, so that's the role of a chiral catalyst. It can allow for the formation of a particular stereoisomer. You're decreasing the entropy. You're decreasing the randomness. Alright, so I'm going to end here as far as our discussion of Chapter 9. I'll do one more lecture regarding alkenes, and that will cover halogenation and hydrohalogenation.